Section 6.2, distinguishing topological spaces via connectedness. Our first exercise here is going to relate boundedness in a metric space to connectedness. So let's first of all review what a bounded metric is. So let XD be a metric space. A subset A of X is said to be bounded under the metric D if there exists some positive real number mu such that mu is an upper bound for the distance between any 2 points X and Y in A. Okay, and if the whole set X is itself bounded under D, then we say that D is a bounded metric. Okay, and presumably any subspace of X would be bounded under D in that case. All right, we're also going to use theorem 6.6. It says if X is connected and we map it by a continuous function f to another space Y, then the image f of X is going to be connected in Y. And basically the reason is that if it were not, then you'd have a separation of it, and you could sort of pull that back and take the pre-image of those two sets in your separation back to X, and the pre-images would form a separation of X, but you can't have one of those because X is supposed to be connected. So, all right, well, here's our exercise. Let B in Rn be bounded in the Euclidean metric. Prove that the complement of B in Rn has exactly one unbounded component. Okay, so there's several things coming together here. Here's my little example. I'm in the plane here in R2, and my B has three pieces, this one, and then it has this piece with a hole cut out of it. So the points in this little region here are not in B. And so the complement of B has how many components? Well, it has basically all the stuff outside of these three, and then it also has that little piece inside here, right? So the complement of B has two components, but only one of those components is unbounded, right? The one outside here. This component here is certainly bounded. Okay. So yeah, it looks like it's true. Although it turns out this statement is only true when n is greater than or equal to 2. Okay. In the case when n is 1, if you have just the real line and you take away some b, right? Take away some bounded subset of the real line, then well, as long as B is not empty, you're going to have two unbounded components, right? One that sort of goes off to the right to infinity and one that goes off to the left. And so it'll be interesting when we finish our proof to sort of look back and see why it would fail in the n equals 1 case. Okay, so to start off, let D denote the Euclidean metric and assume that it is bounded. So we have this mu, which is an upper bound for the distance between 2 points X and Y in B. And we can first of all take care of the case when B is empty, because if it is, then its complement is just the entire Euclidean space, which is connected itself, and if it's connected, then it is its only component. So there's exactly one unbounded component in that case, and we're done. Okay, so now we can assume that B is non-empty, and just to get a handle on it, let's pick a point in it. Okay, so here's my B has these two little pieces, and I'm just going to pick a point B in there. And the fact that this metric is bounded above by mu means that if you take the closed ball of radius mu about this point B, then every other point in the set B would have to be contained in that closed ball, right? Because every point is no further than mu away from B. So I basically found a big ball which contains my set B. Okay. Well, what that means then is that the complement of that ball is a subset of the complement of my original set B. Okay, when we take the complement, the inclusion flips. Okay, if B is contained in the ball, then the complement of the ball is contained in the complement of B. And I'll just note that the complement of this ball is basically all the points in your set X, which I guess I actually mean in Rn. Oops. In n such that the distance from that point x to b is greater than mu. Okay. All right, well, our goal is going to be to prove that Rn minus this ball is connected by, because this is a simpler space, okay, than Rn minus b, because who knows what b looks like. So Rn minus the ball, we're going to show that's connected by finding a continuous function f from this connected space to Rn with this image, okay, which will imply that this image is connected. And we're going to be using this theorem up here, theorem 6.6, where x is r plus positive real numbers cross Sn minus 1, the sort of unit sphere within Rn, and y is Rn, and then f of x is exactly what we want, Rn minus this closed ball. Okay, so to define this function, make this visible, what we're going to do is, well, we have to take an element of r plus cross Sn minus 1. Okay, so we have r, which is a positive real number, and we have y, which is in Sn minus 1, which, remember, means it's a point in Rn, which is sort of a distance 1 from the origin. Okay, so y, you can think of it as like a vector with n coordinates. And all right, here's what I'm going to do. For any particular, so fix some r value, and I'm going to map sort of the unit sphere, map all these different y values. I'm going to take my b, and I'm going to add on, I'm basically going to expand this sort of unit sphere by a factor of r plus mu. Okay, so remember, r is always greater than 0, so this expansion factor is always going to be greater than mu. So what multiplying by this does is it takes the unit sphere and it gives me instead a sphere centered at the origin of radius r plus mu. And I'm going to sort of think of this as vector addition. I'm going to add that to b. So what this gives me is a sphere centered at b with radius r plus mu. And if you take all of those for sort of all positive real numbers r, then you get every sphere centered at b of radius greater than mu. Okay, and the union of all those things is exactly, well, it's exactly what you see here, right? Set of all points whose distance from b is greater than mu. Okay, so well, hopefully I've convinced you that the image of this function f is the complement of the closed ball. Hopefully you believe that f is continuous. If you write it out in sort of components, it looks like this, and it's just built up by addition and multiplication, so nothing too crazy. So we conclude that its image is connected. Okay. All right. Well, that's connected, and remember, it is a subset of Rn minus b. So okay, by theorem 6.12 part 2, there must be a component of Rn minus b that contains this connected subset. And okay, well, that component is certainly unbounded because it contains an unbounded set, right? So we've found that there's at least one unbounded component. Okay? It's the one that contains the complement of this closed ball. Okay, well, let's make sure there aren't any other ones, right? So any other component of the complement of B is, well, it's disjoint from all the other components. And since the complement of this closed ball is contained in one of those other components, the complement of B is, this other component is disjoint from the complement of the closed ball. Okay? And that means that it's contained in the closed ball itself. Okay? Well, that closed ball is bounded, okay? And therefore so is the component that's contained in it. So, okay, well, let's just double check that this closed ball is bounded. If you take any 2 points x and y in it, then the distance from x to y by the triangle inequality is less than or equal to distance from x to b plus distance from b to y. And since x and y are in this closed ball around b of radius mu, each of those distances is less than or equal to mu. So the overall distance is less than or equal to 2 mu. Okay, so this ball is certainly bounded. All right, well, that finishes the proof, except remember, this should only have worked when n is greater than or equal to 2. So let's think about sort of where this would fail in the case when n equals 1. And, well, it turns out that the trouble comes with our function f here. Or, well, more to the point, in terms of, trouble comes with the domain of that function f. Right? I claimed that this was a connected space because R plus is connected, and so is Sn minus 1, and I'm using those facts. And the product of two connected spaces is connected. Okay. But when n equals 1, Sn minus 1 is S0, which is sort of the unit sphere in R1. It's a set of all points at distance 1 from 0 on the real line. And that's just a set with 2 points in it, right? Negative 1 and 1. And that's not connected. In fact, it's sort of it's a 2-point set where those, which is disconnected. And if you do take the product with R plus, then you just get 2 copies of R plus, right? You get 2 rays. And so that has 2 components. Okay, so that's where the proof breaks down in the case when n equals 1.